Good day, everyone. So for today's discussion, we are going to talk about electric potential and capacitance. So at the end of the session, we are expected to be able to explain the similarities and differences between electric potential energy and gravitational potential energy, calculate the electric potential difference between two-point charges and in a uniform electric field, calculate the capacitance of capacitors, and to determine the factors affecting capacitors. So we recall that the change in potential energy of an object that is lifted up to a higher position is the negative work done by a conservative force on it to lift it up, and that is given by the equation delta PE, that's change in potential energy, equals the negative work. So supposing we have an object here, this is our point of reference, this is the ground, and we have a certain object here, and we want to lift it up to a higher position. Now, in lifting this object up to a higher position, work is done on it. But work here is both opposite the direction of the gravitational force. So meaning the work done is negative. So when work is done on it, remember that if we're doing work on something, it simply means that we're transferring energy to it. So in lifting it up, the object gains a potential energy. So the change in the potential energy of this object is equal to the negative work done on it. So we also recall that a conservative force is a force that is independent of the path taken. Its dependence is on the position of the object, meaning its dependence is only on the initial and the final position of the object. So in our example before, we talked about like if you're on the ground floor and you want to go to the 8th floor, so it doesn't matter if you take the elevator or the stairs as long as you're able to get to the 8th floor. So that's what it means. It's dependent on the position rather on the path taken. So just like that, electrostatic force is also considered a conservative force because its dependence is on the position rather than on the path taken, just like the gravitational force. So we can say, therefore, that the change in the electric potential energy of a charge is the negative work done by an electrostatic force in moving it from one point to another. And that is still given by delta PE equals negative work. This delta PE now is the electric potential energy, and this work is done by the electrostatic force in moving a charge from one point to another. In this figure here, we have a positive and a negative plate that are parallel to each other, and we have a positive charge here. So in the change in the electric potential of this positive charge in moving it from point A to B is the negative work done by the electrostatic force to move it from A to B. So from the formula of the electric field, E is equal to F over Q. So F here is the electrostatic force and Q is the magnitude of the charge. So therefore, the electrostatic force can be computed by multiplying the magnitude of the charge times the electric field. So when the charge Q is placed at a point very near a positive plate, just like this one here, it will not affect the electric field since the value of the magnitude of Q is so small. So when Q is released, the force will do the work on it and it will accelerate it towards the negative plate, as in point B. So the work done by the electric field to move the charge at a certain distance, the work is equal to force times the distance. So the force is QE. And the distance, let's replace this to be consistent with the variables. Let's replace that with R. So work, therefore, done by the electric field to move the charge is equal to the magnitude of the charge times the electric field times the distance traveled R. And when Q moves from point A to B, so diba high potential to low potential, so meaning decrease ang ihang potential energy. So when there is a decrease in potential energy of the charge, there is a corresponding increase in the kinetic energy. So as Q moves from point A to B, its potential energy decreases and its kinetic energy increases by an equal amount in accord with the conservation of energy. The summation of the changes of the kinetic and the potential energy, rather, is always equal to zero. Energy is always conserved. So we have to take note also that a positive charge Q has its greatest potential energy near a positive plate, and a negative charge Q has its greatest potential energy near a negative plate. So why is this? So, di ba, for an object that is near the ground, low ang iyang potential. For an object that is far from the ground, high ang iyang potential. So, by nature, object is on the ground. So, for a positive charge, by nature, dapat it should be near the negative plate. The nearer it is to the negative plate, the lower is its potential. The farther it is from the negative plate, the higher its potential. So for a negative charge, the closer it is to a negative plate, di ba by nature, dili man mag-attract ang negative of negative. So high ang iyahang potential. And the closer a negative charge is to a positive plate, the lower its potential. So again, a positive charge has its greatest potential near a positive plate, and a negative charge has its greatest potential near a negative plate. So we also recall that electric field lines are directed away from the positive charge. So the lines are directed from the positive to the negative. So for a positive charge, work is positive if it moves in the direction of the electric field. So here, moving the positive charge from A to B, work is positive. But work is negative if the positive charge is moved opposite the direction of the electric field. So just like here, this positive charge is moved from point B to point A. So against siya sa electric field line, then work is negative. For a negative charge, moving a negative charge along the direction of the electric field is negative. Okay? Kay opposite man siya sa nature sa negative charge. So work is negative if it moves in the direction of the electric field, as in the case here, in moving this negative charge from point A to point B. But work is positive if it moves opposite the direction of the electric field, as in moving the charge from point B to point A. So an electric potential, in continuation, is the electric potential energy per unit of a charge. So for a positive charge Q with a potential energy PEA at point A, its electric potential, by the way, the electric potential, we use the variable V for that. So the electric potential at a certain point A of a charge Q is equal to the potential energy of the charge at A divided by the magnitude of the charge Q. And its electric potential at point B is its potential energy at B over Q. So therefore, the potential difference between the 2 points, A and B, is equal to the negative work done by the electric field to move the charge from point A to point B. So this VAB, or this difference between their potentials at point B and point A, so we can simply write that as delta V. And this is equal to the negative work done in moving the object from A to B divided by the magnitude of the charge. So, problem number 1. The work done by the electric force as the test charge of magnitude 2 microcoulombs moving from A to B is 5 times 10 to the negative 5 joules. So determine the potential difference between the 2 points. So this is very simple. Delta V equals negative WAB over Q. So that's 5 times 10 to the negative 5 joules divided by, what's micro? That's times 10 to the negative 6 coulombs. So meaning the potential is, electric potential as a unit of joules per coulomb, which is equal to volts. And by the way, this is negative, and this is equal to negative 25 joules per coulomb, or that's negative 25 volts. So what does it mean if the electric potential or the change in the potential or the potential difference between the points is negative? It means that the electric potential is higher at A than B. Greater ang potential sa A compared to B. Okay, next problem. An electron is accelerated from rest through a potential difference of 5,000 volts. What is the change in electric potential energy of the electron? Okay, so we're talking about an electron here. And we're trying to find in letter A the change in the electric potential energy. So how do we find the change in electric potential energy? Delta PE. So we are given delta V, that's 5,000 volts, and we're given an electron. So an electron has a charge of, pila may charge ng electron? Negative 1.6 times 10 to the negative 19 coulombs. And what are we looking for? We're looking for delta PE. Okay, so delta PE, so delta V is equal to delta PE over Q, right? So therefore, delta PE is equal to Q delta V. Okay, so that's simply equal to negative 1.6 times 10 to the negative 19 coulombs times 5,000 volts. So our change in potential energy is negative 8 times 10 to the negative 16 was the unit. That's joules. So what does the negative sign tell us? It means that the potential energy decreases. Okay, the potential difference has a positive sign, meaning the potential difference, like in moving this point, let's say for example from A to B, so the final potential would be higher than the initial potential. No, and negative electrons are attracted towards a positive electrode and repelled away from a negative electrode. Okay, next question. What is the speed of the electron as a result of this acceleration? Again, what is the speed of the electron as a result of this acceleration? So let me just erase this. So just recall that negative 8 times 10 to the negative 16, if you can still use that in our solution. So, diba, energy is conserved. So, delta KE equals negative delta PE. So, at rest man initially, so meaning 1/2 mvf squared, no, equals the change, no, in the potential energy, which is, pila man to siya? Negative 8 times 10 to the negative 16 joules. So as a result of the acceleration, the final velocity is equal to, so negative of negative di ay ni siya. So that's it makes it positive. So square root of 2 times 8 times 10 to the negative 16 joules divided by, diba, mag-mass sa electron. So what is the mass of an electron? So you can find this in your calculator. So that's 9.1 times 10 to the negative 31 kilograms. and compute square root of 2 times 8 exponent negative 16 divided by 9.1 exponent negative 31. You will get an answer of 4.1931 times 10 to the power of 7 meters per second. So the potential energy doesn't depend on the mass, no, only on the charge and the voltage. However, the speed will depend upon the mass of the charge. Okay, next problem. Two parallel plates are charged to produce a potential difference of 50 volts. If the separation between the plates is 0.05 meters, calculate the magnitude of the electric field in the space between them. Again, two parallel plates are charged. Let me just solve problem number 3 here. To produce a potential difference of 50 volts. If the separation between the plates is 0.05 meters, calculate the magnitude of the electric field in the space between them. So, bale, if you have parallel plates, say for example, this is a positive plate, and this is a negative plate. So, syempre, the electric field is in that direction, no? And we are looking for the magnitude of this electric field, provided that the difference, no, the difference in the potential is 50 volts between the two plates. And the distance between them is equal to 5 or 0.05 meters. Okay. So how are we to relate electric potential? So we have delta V equals 50 volts. We have a separation of 0.05 meters. And how are we to find the magnitude of the electric field? So how are we to relate that? Right? So diba work is equal to negative Q delta V. Tama? Work is equal to Q negative delta V, negative. But what is work equal to? Work is equal to Q ER, right? So therefore, E is equal to negative delta V over R. Okay? So that's negative 50 volts over the distance of 0.05 meters. E is equal to 1,000 volts per meter. So the direction, the minus sign, tells us that E points in the direction of decreasing potential. So it's just the direction. But if we're talking about the magnitude, so the magnitude lang, so we'll just take the absolute value. So the electric field is equal to 1,000 volts per meter. Or that's newtons per coulomb. So that is our answer for problem number 3. So let's go to the capacitors. Capacitors are devices that are used for storing charges. These are used in motherboards, in photo flash units, and in television and radio circuits. The standard symbol used here is kanisha. Mura siya duha ka parallel, and then naayong ana. So the ability of a capacitor to store charges is its capacitance C, which is equal to the charge over the potential difference between the plates. So C is the capacitance, and the unit for capacitance is in farad, which is equal to coulomb per volt. Q is the amount of charge in one plate in coulomb, and delta V is the potential difference between the plates. So there are many types of capacitors. There's a cylindrical capacitor, but the most common type of capacitor are the parallel plate capacitors. So parallel plate capacitors are the type of capacitors which have an arrangement of electrodes and an insulating material. So the two conducting plates of equal dimensions act as electrodes. So kani silang duhang mga gray. Okay, muna siya ang mga conducting plates. They are parallel to each other. That's why called parallel plate capacitor, no? They are the electrodes. And there is a dielectric between them, which acts as a separator for the plate. So the distance between the plates is given by the thickness of this dielectric between them. So the factors affecting the capacitance of a parallel plate capacitor, so depende kung pilay kaya niya no nga i-store nga charge, will depend upon the following factors. Number 1, the area of the plates. Number 2, the distance between the plates. And number 3 is the type of material used or the dielectric na gigamit. So the dependence of the capacitance upon the aforementioned factors can be mathematically expressed using the formula. So I want you to analyze. Is the capacitance directly proportional or inversely proportional to the area of the plate? Is the capacitance directly proportional or inversely proportional to the distance between the plates? The greater ba the area of the plates, the greater the capacitance, the greater ba ang iyang ma-store nga energy or mas gamay? The greater ba ang distance between the plates, mas dako ba ang iyang ma-store nga energy or mas gamay? Okay, so this is C E A over D, where this is the permittivity of the insulating material or dielectric. So it depends upon the material used. So most materials used are air or vacuum, ordinary glass, Pyrex, mica, mylar, paraffin, polyethylene, porcelain, Teflon, water at 20 degrees Celsius. So lahi-lahi ang permittivity sa material. Depende, no, kung unsay gamit. Okay, let's solve problem number 4. But let us just erase first problem number 3. Okay, calculate the capacitance of a parallel plate capacitor whose plates are 20 by 30 cm and are separated by a 1 millimeter air gap. So capacitance is given by EA over D. So we're talking about an air gap here. So ang insulating material nga gigamit or ang dielectric nga gigamit rather is air, and it's 0.885 times 10 to the negative 11, no? Coulomb squared per Newton meter squared. 0.885 times 10 to the negative 11 Newton meter squared per Coulomb squared. Coulomb squared per Newton meter squared rather. And then the area is, it's a rectangular, so it would be, it's 20 by 30 cm, so that would be 0.2 meters by 0.3 meters. Okay, and the distance is a 1 millimeter air gap, so that's 1 mm, but you have to convert that in meters, and 1 meter is equivalent to 1,000 millimeters. And so the capacitance of this parallel plate capacitor is 5.31 times 10 to the negative 10 coulomb per volt. Or that is equal to, you can just go directly to farad. Farad. Okay, that is letter A. What is the charge on each plate if a 12-volt battery is connected across the two plates? What is the charge on each plate if a 12-volt battery is connected across the two plates? So how are we to solve the charge on each plate? Well, the formula is simple. Q is equal to the capacitance times V. So we have 5.31 times 10 to the negative 10 farad times the voltage of 12 volts. So the charge on each plate is equal to 6.372 times 10 to the negative 9. And this is coulombs. Okay, letter C, what is the electric field between the plates? What is the electric field between the plates? E. So electric field is equal to diba, V over R. So 12 volts divided by, that's 1 times 10 to the negative 3, diba, meters. So 12 divided by, okay, what is the electric field? So it's 12,000. Okay, volt per meter. And letter D, estimate the area of the plates needed to achieve a capacitance of 1 farad given the same air gap. So we are still going to use the same formula, C equals over D. But the air gap is the same, so it's 0.001. The capacitance is now 1 farad, is 0.885 times 10 to the negative 11 coulomb squared per Newton meter squared over area divided by 0.001 meters. So area, therefore, is just equal to 0.001 over 0.885 times 10 to the negative 11 meter squared. And that is equal to that's 1.1299 times 10 to the power of 8 meter squared. And that is the area. Expected nga area needed to achieve a 1 farad capacitance.